Hi, I'm John Boykin from Gilson Engineering. We've developed a utility to assist with programming of various Siemens level controls for common applications. The utility can be used for the Hydranger 200, Hydranger 200 HMI, LUT 400, Probe LU, and various radar products. Besides assisting with the setting up of the program parameters, you can use the program to document your configuration for future reference. Looking at the main page, you notice that we have 6 of the applications are for open channel flow using older and newer style Hydrangers and the LUT 400. The Probe LU and radar level transmitters can also be used, but they do not include the totalization function. We've also included the tab for the OCM3, which has been obsolete for a few years now. You'll notice some applications are for contracted weirs and some are for other than contracted weirs. The equation for contracted weirs is more complex than other primary devices, so we gave it its own tab. Let's start with an example of a traditional Hydranger 200 and an open channel flow application. And in this example, we'll select a 6-inch partial flume with a flow range between 0 to 500 GPM. So I want to start by putting the little bit of documentation information like the date, location, now I want to go to some of the application parameters, and a pretty common sensor for open channel flow is the Model XRS5. We need to select our flume size, 6-inch partial flume. Engineering units will be GPM. Our totalizer, we'll put a 10-to-1 scale factor in there for the totalizer. So the totalizer, each count will represent 10 gallons, and no decimals required. The primary display on the Hydranger then, we can be flow rate or flow total. We'll make it flow total. Now you need to come up here and say what our maximum flow rate is going to be. In this case, it'll be 500 GPM. Even if we select MGD as our engineering units, we still need to select our maximum flow rate in the engineering units of GPM, and the program will then convert that to MGD. After that, the only thing we need to do is to measure the distance from our sensor face to our zero flow point and put that in parameter 006. The Hydranger does not have the ability to calculate flow over contracted rectangular weirs via equation. The equation is just a little bit too complex for it to handle. So in this case, we need to set up a 32-point level to flow linearization table. So once we set up our documentation, and let's call it a 2-foot rectangular weir, a flow rate of 3 MGD. And because rectangular weirs normally have flow rates in MGD, that's what we have as our default units. For our totalizer, since we're in MGD, once we select million gallon per day, the Hydranger sees flow in units of millions and not gallons. So to make the totalizer read 1 count equals 1,000 gallons, we have to tell it the multiplier factor is actually 0.001 or 1,000th of a million gallons, which is 1,000 gallons. It's kind of confusing. But again, once we select million gallons per day as our units, we look at millions of gallons as our base unit, or 1 million gallons for a totalizer, and we have to put a scale factor of 1/1000th to have the totalizer read 1,000th of a million gallons or 1,000 gallons. Pretty confusing, but it actually works out. Now, once we've selected everything, put in our distance from our sensor face to the zero level point, call it 24 inches. We have to come down a little bit further and hit a macro button, calculate maximum head. Once we do this, it sets up a table of level to flow that we need to program into the Hydranger. The Hydranger 200 HMI includes an integral keypad and programs with English prompts as opposed to the function codes used in the traditional Hydranger. It also has a quick start wizard that can be used for setting up the open channel flow applications. In this case, the primary function of the utility is to document the program. Let's do the same partial flume application as we did before. So we're going to choose the XRS5 sensor. Rate of change, which can be slow, medium, or fast, we'll choose medium. 6-inch partial flume. 500 GPM is the maximum flow rate. Engineering units are gallons per minute. Totalizer factor will be 10:1, or 10 gallons per count on the totalizer. And if we want to use a remote totalizer, which uses a relay, we can put in 100 gallons per count for the relay to click. So you can see here, it fills out our program parameters, but instead of having parameter codes P001 through P999, it's all in English. So program these values in, and you should be up and running. The model LU-T400 also uses English prompts for its configuration, similar to the Hydrangea 200 HMI. The LU-T400 is about 80% the same programming as the Hydrangea 200 HMI, but with one big difference. If we take a look at how we program the Hydrangea 200 or HMI, we measure the zero distance from the sensor face down to zero flow point as one value, and then from the zero flow point upward as our span. In the LU-T400, we're a little bit different. We still measure the distance from our sensor face down to the low cal point, which is our zero flow point, but our high cal point is not from our low cal point upwards, but from our sensor face downwards. So again, both our low cal point and high cal point are measured from the sensor face. The probe LU and radar level transmitters can be set up to linearize level to flow. Although the 4 to 20 milliamp output and integral display will show the flow rate, the display cannot totalize. So we're going to do our same example here of a 0 to 500 GPM through a 6-inch partial flume. And for the probe LU, there are no equations built in, so everything has to be through a linearization table. Once we put in our primary device type and our flow rate, everything else is calculated here except for the same thing as before, our parameter 006, which is a measured distance from the sensor face down to our zero level point. But again, we do the full calculation here of level in inches to flow in GPM. Another common application for the Hydrangea 200 is for pump control. With the older style of Hydrangea 200, there are a lot of parameters to configure, so this page should help simplify things a little bit. So in this example, we've got a well with 3 pumps in it, a high-level alarm and a low-level alarm. Once we've done our primary parameters, which are the distance from sensor face to 0 point, which is 4 milliamp, and from 0 point up, which is 20 milliamp, we're going to select our control functions. So in parameter 111, we have 6 choices, 1 for each relay. We'll come to the drop-down menu. So we're going to make relays 1, 2, and 3 operating the pumps, and each pump will alternate. So let's select for relay 1, 2, and 3, alternate duty assist. If you're looking for a more detailed description of all these parameters, just come to this cell right here where we got the red arrow, and we pull up the full description of each one of the control functions that are available. As you can see, the alternate duty assist, that alternates the on and off set points for any relay that is assigned to alternate duty assist control function, and this is actually the most common. So relay 4, we're going to make that a level control, which will be a high level, and relay 5 will be a level alarm also, which is for a low level alarm. Once we've defined our control function, we have to put on or assign our set points for on and offset points. So let's make up an example here. Relay 1 will come on at 4 feet, go off at 3 feet. The second pump will kick on at 6 feet. Also kick off at 3 feet. And third relay will turn on at 8 feet. Off at 3 feet. The fourth relay, which is a high level alarm, is going to come on at 10 feet. Turn off at 9 feet. And the low level alarm will come on at 2 feet. And off at 2.5 feet. Another slick little function we have in the Hydraranger is pump start delay and pump power resumption delay. In pump power resumption delay, say you have a power outage due to a storm, and during that power outage your well's filling up. Now the power kicks on and everyone in the neighborhood, their lights are turning on, VCRs, microwaves are kicking on at the same time. You might not want your pumps to kick on at that exact time because of a potential power surge. So let's put in maybe a 30-second time delay in there that once the Hydraranger gets power back, now we can start actuating these relays to turn the pumps on. And if we don't want to turn all 3 pumps on at the same time, we can put in in this case, maybe a 10-second pump delay so that once the first pump turns on, it'll wait at least 10 seconds for the second one, then 10 more seconds for the third one. That's kind of important because if you do have a power outage for a while, those pumps aren't running, the well's filling up, and you might be at a level where you want to turn on all 3 pumps at the same time, but again, potential power surge could trip things out. The Hydraranger 200 can perform differential level calculations also, and these would be required for applications in wastewater plants, such as traveling screens or bar screens. It's probably mentioned now that only the 6th relay version of the Hydraranger 200 and Multi-Ranger 200 can perform the open channel flow calculations and differential calculation required for these traveling screen type applications. So in this application, we got a traveling screen, and I want to have sensor 1 being the upstream sensor, sensor 2 being the downstream sensor. And what I want to do is have relay 1 alarm on high differential level and relay 2 being on high upstream level. So relay 1, we're going to assign that to looking at the differential between the upstream sensor and downstream sensor. And the second relay, we'll look at transducer 1, which is the upstream sensor. The control function for relay 1, which again we're looking at differential, will be at level. So we want to look at the level difference between upstream and downstream sensor. And relay 2 will also be a level, but that's absolute level and not the differential, just absolute level, so that when we get to a certain high level, we want to turn the pump on or turn the screen on to get all the debris out. What we'll also want to do is tell the Hydraranger to assign the analog output not to sensor 1, sensor 2, but to the differential. And to do that, want to select the differential as the output allocation. So down here in parameter 202, we put in the value of 3. And again, we need to do that if we want to have the 4 to 20 milliamp output from the Hydraranger be assigned to the differential. Well, we've been telling you how great this program is and how can be used to help you set up your Hydrarangers, LUTs, and probes for some common applications. Now I'll tell you how you can get it for no charge. Want to go to the Gilson Engineering website at www.gilsoneng.com. And the quickest way is just scroll over to the actual Hydraranger on the wall right here, camp on it, click Quick Parameter Setup Program, and you can either save or open. In this case, I'll open it up. And there we are. You can save that to your desktop. Hope this helps with your setup of the Siemens Level Controls. Thank you very much.